Valentina, thank you very much for the invitation to participate in this summer school and to present some of the work that we are doing in our lab. I'm Mariana Damova from Mosaic, the Humanizing Technologies Lab in Sofia. My talk is going to be about semantic information infrastructures, where I'm going to discuss their value to data-intensive services, and I will show a variety of examples where these infrastructures have provided competitive advantage to the entities that have adopted them, the organization that have adopted them. And we have to bear in mind that actually these technologies have blended into the Google search service and for about 5 years now, and thus they have become ubiquitous commodity for all of us. However, linked data technologies and semantic infrastructures have their role to play in virtually all economic domains. I will show some of them in this talk. But let's first start with the motivation about the existence of semantic web technologies. And I cannot switch the... Okay, the motivation about semantic web technologies. Here you see a brief evangelization about the benefits and advantages of using semantic web technologies. So Ginny Rometty, the president of CEO and CEO of IBM, has claimed that data is the world's great new natural resource. What steam power was to the 18th century, electromagnetism to the 19th century, and fossil fuels to the 20th century, data will be to the 21st century. The statistics show that by June 2020, the web counts 5.41 billion pages and 1 million exabyte storage capacity of the internet. The global traffic is expected to hit 333 exabytes per month by 2022, and the computing capacity increases exponentially almost every day. The web is not the only source of a lot of data. Statista shows that there are 35 billion devices connected to the internet, and the automotive industry alone will produce 110 million new light vehicles that will comprise 200 sensors per car, which makes about 22 billion sensor producing data this year. In Industry 4.0, further, envisages to digitize the entire product production life cycle that fully involves intelligent handling of data. To be able to manage this vast amount of data and make something reasonable with them, a number of approaches related to AI have been developed. The most popular ones in the last decade have been the different flavors of machine learning, supervised, unsupervised, and deep learning. However, their advances raise the issue of explainable AI, as the humans lost control in the decision-making process of the algorithms, and the need arose for humans to be able to understand the way algorithms make decisions to make sure that AI won't take unethical or harmful decisions and actions. That is why the European Commission has initiated this initiative of creating guidelines for an ethical and trustworthy AI as a brand for the Made in Europe AI. The main characteristics of this kind of AI require it to be first lawful, respect all applicable laws and regulations, second ethical, respecting ethical principles and values, and third robust, both from a technical perspective and taking into account its social environment. These guidelines were translated into 7 key requirements that I'm going to list right now. For example, human agency and oversight, technical robustness and safety, privacy and data governance, transparency. Oh, sorry. Excuse me. I lost the. Can I please stop the presentation so that I can do the slideshow properly again? I apologize for this.
Okay, sure.
Overall, these 7 requirements call for explainable AI because all of them show the need for us to be able to know how decisions and conclusions are being drawn by the algorithms. So I'm going to speak here about the semantic web and linked data technologies as an AI technologies that produces explainable AI and an instrument that allows the creation of intelligent infrastructures for information and data management at a web scale while preserving the explainability of the reasoning processes as they are based on principles of formal logic. To summarize this information, the semantic information infrastructures built with these technologies allow for easy interlinking of data, efficient storage, data interoperability, and are very easy to extend. The underlying schemata of the semantic infrastructures are ontologies, conceptual models representing entities and relations between them. And here you see listed the advantages of using the semantic infrastructures. They are schema agnostic. Unlike relational databases, the same logical data format is used to describe the models and the instances of the data. The examples on the slide show how the schema and the data of a relational database enter into one and the same representation format, the graph to the right of the slide. These graph structures enable to break data silos by creating interfaces between the separate legacy databases to make all information become a single graph of interconnected nodes, and thus enable federated search of information from multiple sources. Federated queries can be of use for federating data from departments of factories and enterprises, consulting variety of information for drug production, federating and aggregating data for autonomous car driving or traffic management, etc. Semantic information infrastructures integrate semantically data of different sources and nature, relational databases, spreadsheets, text documents, file systems into a single connected graph with explicit links between the well-defined semantically objects. This network of connected objects allows the application of methods to search, compare, and browse the graph in explainable manner. They allow for distributed knowledge discovery as they provide with an ambiguous way to get to the information regardless whether it is located on a server next door or on a server in a different country from a single access point. For instance, in the cultural heritage domain, the network of linked objects can describe a manuscript linked to its author, the author to his birthplace, and other artifacts that belong to him, the whereabouts of these artifacts, in particular museum, etc., etc. And all this information can be dislocated in space. The semantic infrastructures based on linked data or networks of connected objects can be applied in two modes: in user-facing applications where semantic search is being performed, or in their machine-readable mode as modules of larger systems where the network of connected objects drives the flow of the system. Here are some examples from Industry 4.0 domain, where we can imagine these graphs, the browsing, the navigation through such graphs of connected knowledge can answer. For example, we can ask questions about the operations director of a factory can ask a question like, can I produce this machine by this date? Or do I have enough resources in stock until the end of the trimester? And obtain straightforward answers to them at the click of a button. The same semantic infrastructures can be applied in robotics as a smart embedded devices to drive, manage, and control the workflow of a production line. Speaking of machine-readable applications, one can imagine engineering processing car design that employs ontological models to connect the car tails, or in a production context to launch alerts or warnings, or to obtain instructions to switch on or switch off of a given equipment. The reference architecture with semantic web layer consists of a web of data layer that integrates data from different sources and formats in an information uniform semantic graph, and making them useful and usable by other modules. The figure on the slide shows how data from multiple sources get integrated into a single common graph structure. And now come different applications that we have done in Mosaic with using these kinds of infrastructures. Industry Inform is one of Mosaic's commercial offering for business information delivery. It is based on semantic infrastructure, collecting information from different sources, public and private databases, web and social media. And it allows search for information in a Google-like manner or with parameterized criteria. Here is the query about the phone numbers of companies in Sofia with revenues about above 5 million Bulgarian leva, and the results come in the following way. The phone number is on the second line of the results. In the archival domain, semantic infrastructures can be applied to expose the archival data to the general public, enrich with external to the archive information. Thus, the linked open data archive prototype of the historical archive of the European Commission is another project that we carried out last year. Here we show examples of queries that link objects with their occurrences in the titles or descriptions of the archival records. And if you go to the site hasmosaic.co and do some example queries and navigate, you will discover information about politicians or European institutions that come from outside of the archive of the European Commission. Best practices of modeling ontologies and building semantic information infrastructure is the reuse of existing vocabularies. Thus, in this prototype of the historical archive of the European Commission, we constructed a knowledge base of 23 million statements, where we used 8 ontologies, 1 original that we crafted, and 7 from the linked open data vocabularies, including the semantic technology stack, and 10 data sets from the historical archive, from the publication office, and from the linked open data cloud. Here is the numbers show that out of close to 10 million explicit statements, we derived automatically 13 million more statements available for querying due to the properties of the semantic and linked data technologies. These two examples show semantic data integration and search in two domains using the reference architecture of the semantic web. And here is a distributed service-oriented architecture for an application using semantic infrastructure as a semantic data lake to semantically integrate satellite, geospatial, numeric data, and domain knowledge, harvesting data from a data access layer, here on the bottom, and augmenting it with intelligence that drives the interaction with the users and with the components of the system. These architectures has been implemented in another project of Mosaica that we carried out with the European Space Agency. This project is an example not only of one-of-a-kind semantic data integration, but also an example of hybrid reasoning between deep learning and logical inference. That is why I'm going to present the project in a larger detail here. Here is the motivation. Water resources managers use daily collected information about the condition of the dams, water economic data, meteorological data, weather forecast, geospatial information, and information about the integrated nature environment of the dams. They need to have an overall view of this heterogeneous data and their interconnectedness to be able to analyze, evaluate the situation, and make decisions. This information is heterogeneous, spatial, numeric, symbolic, and images that is very hard to encompass in an overall view or perspective. So we adopt linked data technologies to semantically integrate data about hydrological objects, in situ measurements, GIS descriptions, geospatial information, and satellite data. And we built an ontology based on inspired hydrology model that encompasses all these data from GIS, from satellites, in situ measurements, and domain knowledge. It created a semantic infrastructure that mixes them all in a network of connected objects, semantic graph, with the intention to apply consequently intelligence on them by calculating forecasts about water balance and snow stock and mixing them with logical reasoning about hydrological objects and measurement types. The project delivers semantic search and querying capability over heterogeneous data, demonstrating the method of breaking the silos between these different data. The ontology consists of 74 classes and 53 properties and blends all semantic elements mentioned that I already mentioned. The satellite data come from Adam, our Austrian partner, Sistema. Adam is a data as a service platform providing findable, accessible, interoperable, and reusable satellite data. Here are the data collections that we have used for the project. As you can see, they come from different satellites on the one hand, and for some meteorological features like precipitations, we have used information from different satellites with different resolution, spatial and temporal. And here is how the satellite data look like on the GIS component of the system, provided that each data set that you saw on the previous slide comes in a different color with the intensity of the pixels corresponding to the particular numerical value that they represent. The GIS component is a S3 ArcGIS server, an integrated web application that shows the hydrography of Bulgaria on the one hand, the satellite images, the georeference data from the intelligent layer, and the minimum, maximum, and average values of the satellite data. And this application is integrated with the graphical user interface of the system. The geospatial data flow looks like this. The satellite and the geospatial data are actually part of the data access layer and communicate with the semantic layer, where they are converted into semantic format on the one hand, and with the GIS component, where they are pushed to the graphical interface of the system at the instructions of the intelligent layer. The link between the intelligent layer and the GIS is semantic, as they communicate with the geospatial data alone. The direct link between the satellite data and the intelligent layer is due to the system's forecast modeler, as we skipped converting all the pixels into semantic format, although we made the model for this conversion. And here is what the intelligent layer does. It generates the queries, the semantic queries, it manages the queries, it orchestrates the navigation of the GIS component and the graphical user interface, and it also hosts the forecast modeler. It forecasts meteorological features, actually not meteorological features, but rather water economic data, with importance for monitoring of the water levels of the dams, water resources of the dams, like water volume, water level, water equivalent of the snow stock inflow, with 30 days ahead. For this forecast, we used the neural network models based on historic data from the satellites. They are given here on the slide. And in situ measurements in combination. We carried out different experiments with this respect, and the outputs of the forecast are pushed into the semantic layer, which makes available possible to generate queries about future times, like the one shown here, expected volume of cascade order for the future date, where we obtain results for all the dams that are part of this cascade. This is the user interface of the system, showing how several query parameters can be specified, and the results in the table on the left are synchronized with the data shown on the map. The query asks for precipitation, and the map shows the precipitation layer, whereas the table shows numeric values about the precipitation. Now, if we are lucky, I'm going to show you the a video that shows the system. So here we have water balance, where we see the tables with forecasts for volume and for the day, the current day, the monthly data, again with forecast, and the yearly data, where the map already shows precipitations for the 3 dams. Here we have shortcut buttons that allow quickly to obtain results about the particular feature, graph view, and here the parameterized search. We are going to ask about the inflow of dam Kerjeli when the volume of the dam was greater than a particular value for a given period of time. Here in the result, the map zoomed to the dam Kerjeli, and we see the values. Then we ask how about the precipitations, and the map is showing the layer with the precipitation of a and the legend shows the amount of precipitation. Now here, navigating the map, we can change the satellite. and see another satellite data. And this is the numeric value with the minimum maximum. Then we go to keyword search. We ask about river Arder, and we obtain information about from Wikipedia, and the map is also synchronized to the catchment of river Arder. For the snow stock, the functionality is similar, only here we ask about the water equivalent of the snow stock and the snowfall in December 2016. The precipitations are again in blue, but it is about snow. You see in the different satellites. Then interrogation of for a future date comes. The volume of a different dam, and here you see we obtained automatically alert about danger for overflow of the dam gradually in a future date. I hope to have shown you with these examples the specifics and the essence of the advantages of adopting semantic web technologies and building solutions based on the semantic information infrastructures. And here a little bit about Mosaica. Mosaica is a humanizing technologies lab. At Mosaica, we are trying to leverage data science with natural interfaces to provide solutions tailored to human behavior, attitudes, and comprehension. And here is a selection of our clients and partners. And I thank you for your attention, and I'm available for a question if there are any now.